Hello students, I am Professor Ambika Devi, Assistant Professor of Physics, Government First Grade College, Bidar. Today's video is related to session 32 of BSc 5th Sem Solid State Physics course, which is prescribed in the colleges affiliated to Karnataka State, Gulbarga University, Kalburgi. So, let us now begin with the session 32 of BSc 5th Sem Solid State Physics course, and this session is related to hysteresis curve. There is a process we are applying magnetizing force with the help of current or whatever it is, and this applied magnetizing field is represented by H, and the magnetic field which is developed inside the ferromagnetic material is represented by B. Here we are making a graph of B versus H. This curve is known as hysteresis curve or BH curve. Students, and this hysteresis curve is also defined as the phenomena of lagging of flux density behind the magnetizing force in ferromagnetic materials. These ferromagnetic materials subjected to cycles to magnetization is known as hysteresis, and the term hysteresis is derived from Greek word. Its meaning is lagging behind. This hysteresis loop is explained by this figure. See here in this figure, uh, ferromagnetic material, all ferromagnetic materials exhibits the phenomena of hysteresis. To give a better understanding of the concept, we will take an instance where ferromagnetic substance is placed inside a current carrying coil. Due to the magnetic field, the substance get magnetized in the positive direction. If we reverse the current, then the substance get demagnetized. So here magnetization and demagnetization are takes place. This process is known as hysteresis. See here in this figure shows the behavior of a ferromagnetic core graphically as the relationship between B and H, where the graphical representation is a non-linear, that is curve, starting with an unmagnified core. Starting with an unmagnified core, both B and H will be at 0. At the point O, this is represented in the point O. If the magnetization current I is increased in the positive direction to some value, the magnetic field strength also increases. See, this is the magnetic field strength. H is increases. As H increases linearly with I, then flux density B also increases. This is shown in this figure. From here 0 to A. H, B and H both are linearly increasing as I increases. This point A is known as saturation point. Next, if the magnetizing current in the coil is reduces to 0, see here in this direction. When this magnetizing current in the coil is reduces to 0, what happens? The magnetic field circulating around the core also reduces to 0. H becomes 0, but this flux density has some value. The coil magnetic flux will not 0. Why? Because of the residual magnetism which is present within the core. That's why B has some value. It does not reach to 0. And is shown, this point is represented by B. At this point B, H becomes 0, but B has some value. To reduce this value to 0, what to do? To reduce the flux density at a point B to 0, we need to reverse the current flowing through the coil. We need to reverse the current means its direction changes from positive to negative direction. The magnetizing force which must be applied to null the residual flux density is called coercive force. This coercive force reverses the magnetic field, rearranging the molecular magnets until the core becomes unmagnified. The core becomes unmagnified means at that point B also reaches to 0. As increase in the reverse current means in the increase in the reverse current means here we are increasing current in the negative direction, causes the core to be magnetized. But in what direction? In the opposite direction. Why it magnetizing in the opposite direction? Because here we are applying the reverse current and increasing the magnetization current further will causes the core to reach its saturation point. It reaches the saturation point. Saturation point is here from this point to from point C to D. From point C to D, both are increasing. Both are B and H are increasing means there is a magnetization process and it reaches to some value. It increases and it reaches some value. That point is represented by E. So here this point is similar to A. A and E both are same saturation points, but A is in the positive direction and this point is in the negative direction. If the magnetizing current is reduced again to 0, this is reduced again to 0, what happens? The residual magnetism present in the core will be equal to the previous value, but in reverse direction. Okay. Then again reversing the magnetizing current flowing through the coil. Again reversing this current, then what happens this time? Into here we are applying the current in the positive direction, will causes the magnetic flux to reach 0. Magnetic flux reach to 0, but at this point H has some value point and it is represented at the point F on the curve. As before, increasing the magnetization current further in a positive direction, if we increase the current in the positive direction, then here B and H both are increases and reach this value at a point A. Again it reaches the saturation point at A. Then the BH curve follows the path of A, B, C, D, E, F, again A. As the magnetizing current flowing through the coil alternates between positive and negative values, such as the cycle of an AC voltage. This path A, B, C, D, E, F, A, this path is called magnetic hysteresis loop. So, in a hysteresis loop, magnetization and demagnetization takes place under the magnetizing field. Okay, up to this we have discussed about the hysteresis loop. Then in the next slide uh, we will discuss about energy loss. Energy loss due to hysteresis curve. See here we will derive an expression for total work done or energy consumed during one complete cycle of magnetism, that is equal to total area enclosed by the hysteresis loop. To derive this expression, that is energy loss due to hysteresis curve, we will consider a ring of a ferromagnetic specimen of whose circumference is represented by L meter and its cross-sectional area is represented by A, that is measured in terms of meter square, and it has n number of turns of a wire. So let us consider the electric current flowing through the coil is represented by I, which is measured in amperes, and the magnetizing force is given by this expression, that is H equal to Ni by L. By using this expression, the electric current flowing through the coil is defined as I is equal to HL divided by N. Then according to Faraday's laws of equation, according to Faraday's law, we know that induced EMF is directly proportional to the rate of change of magnetic flux, that is E is equal to d phi by dt. And also flux is given by total flux through the ring is given by phi is equal to B into A, which is measured in Weber. As the electric current flowing through the solenoid is alternating, then the flux produced in the iron ring is also alternating in nature. So the induced EMF will be expressed as E is equal to N d phi by dt from Faraday's law of electromagnetic induction. E is equal to d phi by dt. E means induced EMF and d phi by dt. Phi is the magnetic flux. Then according to Lenz's law, this induced EMF will oppose the flow of current. Therefore, in order to maintain the current I, that is I in the coil, the source must supply an equal and opposite EMF. Hence, the applied EMF is given by E is equal to NA dB by dt. The energy consumed in short time time interval is dt, during which the flux density has changed, and it is given by E I dt. After substituting the value of EMF, electric current flowing through the coil, that is I, then we get this expression, that is NA dB by dt I into dt. So after some mathematical simplification, finally we get this expression. Okay. Thus, total work done or energy consumed during one complete cycle of magnetism is given by W equal to AL is an integral from 0 to B maximum H into H dB. Now, AL is the volume of the ring and H dB is the area of the elementary strip of BH curve, as shown in the, which is shown in the figure. Okay. And lastly, we get this final expression. Total energy loss due to hysteresis curve is given by total area enclosed by the hysteresis loop. Next is significance of the hysteresis curve. The shape and size of the hysteresis loop already depends upon the nature of the magnetic material. The choice of a magnetic material required for a particular application often depends upon the it depends upon the shape and size of the hysteresis loop. And the smaller the hysteresis loop area of a magnetic material, the less is the hysteresis loss. And so here energy hysteresis loss depends upon the area enclosed in the hysteresis loop. So students, I am sure you now got good understanding of the concept of hysteresis loop. I hope all of you enjoyed this session. Thank you.